Okay.
Hey, can you hear me?
Yeah. Can you guys hear him?
Fantastic. I feel slightly perverse giving a talk on holoportation whilst hoping that Skype doesn't break down. Great. Okay, let's get started. Great, so this talk is about holoportation, work that was conducted at Microsoft Research. As you can tell by the author list, pretty much everyone at Microsoft contributed to this work. It would actually take me as long as the whole talk to read out the author list. I did want to highlight these main contributors to the project. Sadly, none of them could attend because they're actually heads down working on the future, basically. So apologies for that. And also apologies that I couldn't make it. I'm really missing you guys, and I've heard it's an amazing UIST, so I wish I could have been there, but there was visa issues. Okay, so for many years, Hollywood has been tantalizing us with the idea of virtual teleportation. This gives us the ability to see, hear, and interact with live holograms, quote-unquote holograms, of remote users as if they're present in your space. In fact, most movies have replaced 2D video with this type of immersive communication. With this capability, Yoda can hold court at the Jedi Council without leaving his swamp. And Princess Leia can leave a holographic voicemail for her friends. But despite amazing research in this space, this scenario is still science fiction right now. So as I said, there has been great research, and there's what I would call some of the early work was actually heroic in terms of how they tried to tackle this problem. One of the projects that I wanted to mention back in 1994, Henry Fuchs and Takeo Kanade had a vision where a patient on the operating table could be captured by a sea of structured light cameras, and their point cloud could be rendered to a remote doctor wearing a head mount, and the head mount was head tracked using a Polymus-like sensor. And although this tech was incredible, the quality of the reconstruction really did let down the end user experience. And that's something that's really followed throughout the work in the early 90s. Systems were really suffering from poor reconstruction quality, as you can see on the bottom right, latency and clunky headgear, as well as lots of infrastructure and cameras. With the advent of Kinect, cool research systems began to look at the notion of telehumans for live remote collaboration. For example, this from Roel Vertigel's lab. And in this case, a cylindrical display and head tracking allowed perspective-corrected imagery in 3D for the user. But again, the quality was low here. Room to Room looked at a projector-based system to remove the need for headwear, but again, the focus wasn't on high-quality capture, as you can see here. And perhaps the closest work to ours is from Henry Fuchs' lab, where a custom AR headset and multiple Kinects were used to capture and render a person in real time. But again, this system, as you can tell, suffers from temporal artifacts, and the head tracking was brittle. So why is it so hard to recreate this notion of the Jedi Council? Well, Henry Fuchs in his seminal work sums it up quite nicely. There's two components to this scenario. There's the real-time 3D human scanning and the head-worn display, which includes head tracking for rendering perspective-corrected graphics. Luckily, this one part of this puzzle has already been close to being solved. This year, we really saw consumer AR and VR really taking off. And there's many VR and AR headsets now providing high resolution and high refresh rate displays, even if field of view is limited in certain cases. In addition, most of these higher end systems also provide 6DoF head tracking. So part of that puzzle has been solved. The other part, the real-time scanning of humans, is still a very hard problem. And that's the problem that we're focusing on in holoportation. So why is this kind of 3D reconstruction hard? High quality capture of humans hard? There's actually 4 reasons that I wanted to briefly touch upon that really make this a challenging problem. The first is that off-the-shelf sensors often fail at providing high-quality reconstructions. In this example, what we did first with holoportation is actually place 8 Connect V2 time-of-flight systems in our capture space. And the output reconstruction is shown on the right. As you can see, the reconstruction quality is really low. It's just not good enough for this kind of teleportation scenario. So what about pre-scanning a person or some other prior model? And in this example, we're actually using the head pose and controller pose of the Oculus or the Vive and an inverse kinematics model to rig the model. And that's exactly what a lot of social VR technologies, such as high fidelity in this instance, do. The problem here is that the humans are complex to model, and so you soon fall into the uncanny valley. The parametric model and tracking technology is never quite rich enough to really model all the pose, shape, or deformation space of the human body. Even with the latest state-of-the-art tracking technologies, here, for example, Michael Black's group at MPI Tübingen, you can see the models still look very uncanny. Instead, we need a model that reconstructs the human body online and is far more driven by the data rather than this kind of parametric model. So one other reasonable question here is, what if you try to rig avatars to provide this kind of experience? And that's exactly what was demonstrated by the social VR demo from Facebook. Well, whilst this might make a cool demo, imagine if you're represented as a cartoon avatar in a business meeting, or if you want to talk with family members and all you can see is this cartoon-like representation. It's just not rich enough for human-to-human connection. So this problem of human capture has been studied at verbatim in the SIGGRAPH literature. Paul Debovec's group at ICT, products from Microsoft last year, ATI and Uncorporeal have all demonstrated high quality offline capture. The problem here is, these require quite large studio settings, lots and lots of controlled lighting, lots of cameras, and they assume a large amount of compute and offline processing, typically requiring all of the frames to be accessible, the whole sequence to be accessible. So it's not real-time and very expensive. To give you one example, the latest state-of-the-art work from Microsoft requires a studio with 160 cameras and 30 minutes per frame, rather than 30 seconds per frame. 30 frames per second, sorry. Instead, with our system, we want to support any arbitrary environment with less infrastructure, and in this case, only 24 cameras and in real time. So 30 frames per second, not 30 seconds per frame. So just to be clear on how our system works, we have a number of custom depth cameras in our environment. I'm being captured in real time, as you can see in the screen in the back. Then in a separate space, another user is being captured in real time. Both our meshes are being streamed from one space to another. And when we wear our HoloLens or any other VR, AR device, we can see each other in each other's spaces. As we move our head, we see the remote person rendered from the correct perspective, and that's what you're seeing in the bottom left-hand corner as shot through the HoloLens. So here's another example here. Sorry. So here's another example here. And you can see the two people are interacting. And in this instance, notice that the system doesn't discriminate between what's being captured in the scene. So you can actually see the user is able to pick up an object on the remote side and have it scan instantaneously so that he can show it remotely to his colleague. As you can see here, the reconstructions are of high quality. There's minimal temporal or spatial artifacts. And to achieve this, we've had to solve 2 major problems. The first is a new type of depth camera that we've created. And what you're seeing here was IR images captured from that image. The second is a temporal reconstruction algorithm that allows the full model to be fused temporally over time. The third piece is the rendering that happens on the remote side. And I'll cover each of these pieces, but in particular focus on the main contributions, which is the depth camera technology and the temporal capture. So first, the depth technology. So our depth camera comprises of two IR cameras, a structured light projector, an and an RGB color camera for texturing. So at each frame, we have a current set of observations, and we know the reference pattern that we're projecting. If we zoom into this pattern, what we have to do now in this calibrated framework is try and match a patch in the observed image to the reference image on the left-hand side. And this is similar to stereo matching. Once we have this match, we can estimate the disparity between the two images, which is inversely proportional to depth, if we know the focal length and the baseline between the cameras. But this is an expensive process. Typically, what has to happen is for each patch in the left image across the epipolar line or across a scan line, we have to match and compare to the current pixel and patch in the current observation. And this is an expensive process that takes a lot of compute. So to solve this problem, there was an intuition that we had. The reference pattern is actually fixed. And that allows us to take the current observation, and just by looking at a patch and trying to recognize that patch, we can directly map it to the reference pattern. And that's what we're doing here. Once we recognize the patch, we can actually directly estimate the depth. So in this example, I'm going to walk you through how we do this. We take a patch, we then use an ensemble of random forests, and we look at pixel offsets between the central pixel and a random set of offsets that are picked at training time. Based on a threshold that's learned at training time, we either go left or right in the decision tree until we hit a class label which recognizes that patch. And that maps directly to disparity. On top of this, we regress a subpixel value to get subpixel refinement of the depth. So that's the depth algorithm. It's actually trained off of ground truth sequences, as you can see here. And one of the interesting learnings is that we perform better than the ground truth data. In particular, if you notice, we don't have fattening effects and holes in the image. So beyond this, once we have the depth map from different viewpoints, if we stitch the data together, it's still a noisy point cloud. We still need to do smoothing on top of this. So now this is what we're showing you here is a fused reconstruction using Connect Fusion from the different viewpoints. And you can see that's still not enough. We need temporal consistency. And that's what we're demonstrating to you here. It's a large part of the framework. And you can see this really removes temporal flicker and high spatial noise in the image, in the reconstruction. So that's the volumetric fusion step that I'll just touch upon. So the volumetric fusion step is actually very much related to work that we showed called Connectra, where we scan in a 3D model and bring it to life using the Connect skeleton. So this technique was quite interesting. So we have a pre-scan of a 3D model, we have a deformation graph, and then when the Connect skeleton is tracked, the user embeds themselves into this deformation graph and says possess. And then when the Connect is tracked and the body skeleton is moving, we know that certain nodes in the graph should move in a certain way. And we can globally optimize the remainder of the deformation graph to be as rigid as possible, to preserve the structure. And that's what we do in the non-rigid fusion step. So here I can show you a number of examples. So here we have first the source volume. We then extract a mesh using marching cubes. We then want to align, instead of to a skeleton, we want to align to the data points coming from the point cloud that we're estimating. We create a deformation graph, and then we deform the deformation graph to as best as possible fit the data, using closest point data association between the point cloud and the deformation graph. Once we have this, we can deform the TSDF grid into the data and fuse at the data volume. Here you can see the non-rigid fusion in action as it's aligning over time. So what we're doing here is we're taking an ED graph made up of a affine transform, a translation, and a node location. We're then mapping that to the marching cubes mesh using linear blend skinning. And then on top of that, our objective function is made up of a data term, which tries to minimize the reconstruction error or the alignment error from the model points and the data points. And on top of that, we have a regularization term that tries to maintain local rigidity. So ignoring some of these equations, what we're trying to do here is minimize the rotation that we get from the affine transformation A so that we minimize stretch and maximize the rotation between node points. And then there's a smoothness term that tries to maintain consistency across pairs of nodes. So here's some results that you can see with our system. You can see the reconstruction quality is able to reconstruct clothing and fine deformations. Our system is also able to reconstruct non-human examples because we don't use a skeleton prior. So here we can reconstruct animals, for example, as well as humans interacting with one another. So the final step that we perform is to compress and stream the mesh over to the remote side. And on the remote side, we do a rendering step that tries to minimize the amount of swimming artifacts that you get on the rendering side. And this is a trick that we apply because we have to remotely stream the data from a PC that does the actual model rendering because the HoloLens doesn't have the capabilities to render it at high quality. So in this example, what we're doing is we're actually streaming that data over to the HoloLens, and then we're actually taking the final pose and warping the image to reduce latency to the viewer. As you can see, this gives a much better artifact-free experience. So some usage scenarios here. So imagine a business meeting where you can beam from one space to another and really not have to get onto a flight to meet. Or in this example, it could be a public event where the person is being captured, like a musician, for example, and beamed into a space where they can interact with the people. Or a boxing match, for example, or another sports match, which is being captured remotely and streamed over to the remote side. So there's a number of challenges that I wanted to touch upon before wrapping up. And these are challenges that are really relevant for the community as a whole. And are direct things that are limitations currently of our technology, but things that should be worked upon in the future. The first is field of view. There's an elephant in the room, obviously, with the HoloLens field of view. And that really does break the illusion of the person being present. As you can see here, when the person is fully within your field of view, it does give the illusion that they're actually present in your space. But when the field of view is limited, it really does break the illusion, and it does feel like sort of a video conferencing-like experience. So that's one challenge. And one of the things that we have worked on here is to actually give support other devices beyond augmented reality devices. So in this example here, you can see a VR device, an Oculus, that we can use. And what's nice about VR is you actually see your own body in VR. So there's an extended sense of presence. And on top of this, the remote person can beam in and you can interact with them, as well as see your own body. Another challenge is around infrastructure. Currently, we have heavy use of infrastructure, not as much as a studio setting, but still heavyweight infrastructure. There is work that's emerging that's trying to do real-time non-rigid capture using single cameras, such as the work from Zollhofer from SIGGRAPH and Newcomb from CVPR. The problem with these systems is they're very brittle in terms of tracking. And in fact, we compared the algorithms to our own system. They don't really handle fast frame-to-frame motions. So there's a lot of work to be done still in this space. Another big sort of elephant in the room is around headset removal. If we're all wearing headsets and trying to collaborate, especially if some of us are co-located, this is not a very enticing experience. And there's been some great work here on headset removal that's been done at SIGGRAPH Asia from Hao Li's group, for example. But here they're using a parametric model of the face, so they can rig other types of avatars, but not give you a sense of actual high fidelity reconstruction of the actual viewer that you want to see. And so we did some early work in this eye by having cameras embedded into the headset, pointing directly at the eyes of the user. And you might imagine in the future that eye tracking cameras can provide that level of sensing. And what we're doing is we're taking visual features on the eye and actually now taking the pose of the device per frame based on those visual features of the eye, mapping it to a pre-scan of the face, and having that in-painted onto the reconstruction. And then the final piece is really around compression. There's a huge amount of data being passed around. So the raw data in our system is around 23 gigabits per second. With compression, we can reduce that down to 1 gigabits per second, and that's our current system compression. It's still not enough for HD video across standard internet. So what we want to do in the future, and I think this is an interesting area of research, is to exploit the temporal consistency and to build up a texture atlas as well as compress the mesh over time. So these challenges really are sort of pivotal challenges in terms of making scenarios like holoportation a reality. And with that, I would love to take your questions. Thank you for listening.
Any questions?
Hi, this is really great and inspiring work. So I just wanted to thank you for doing this. I know it must have taken years to get to where we are now. I wanted to ask sort of a broader question about how this future might interact with the future of mobility. It seems like the world and everyone within it are now moving to a mobile experience in which they can take their computation with them wherever they go. So it seems like the experience that you've shown here is very firmly fixed within a rigid environment in which you can set up cameras in distinct knowable locations. Can you describe what it might be like to experience this in a mobile situation? How might I instrument in my environment mobily, or what does the future hold for people that don't want to be tethered to a specific space?
Jeff, I think I got the gist of that. That was really hard to pick up. Let me just repeat the question and see if I understand it correctly. You were saying, what about mobile scenarios and sort of infrastructure-free scenarios when you're on the move, and how that experience could feel potentially?
Yes.
Great. That's a really great question. I mean, it's actually a scenario that we've thought about. Obviously, you can't carry this kind of infrastructure with you. Maybe with a single camera, you might be able to do something like, place the camera in the scene prior to being captured. But a lot of these devices that are emerging, these augmented reality and VR headsets, are starting to have embedded cameras within them. So for example, there's cameras that provide eye tracking in some of the latest headsets, which see the face. There's a camera, typically, for example, on the HoloLens that looks down and sees your hands. So what you could think about is a scenario where you have a prior model where you've reconstructed the user previously, maybe a very high fidelity, and then using these sparser sets of inputs, you might be able to sort of paint in the missing details. So imagine, you're capturing the upper half of the body using a depth camera on the headset, the eyes of the viewer, so you can in-paint that region, and then maybe there could even be wrist-worn devices to do more effective tracking. The IMU on the headset can give you a sense of the gait of the user, and then you can reconstruct the rest based on a prior scan of the model. But really opening up mobile telepresence in that way, immersive telepresence, could be huge. And it's a nice feature of devices like HoloLens that they're fully untethered.
You talked about using the hyperdepth method for depth sensing. I'm wondering how you addressed interference between the different RGBD pods.
Wow, I'm really struggling to hear. Is it possible to repeat the question, Jeff?
Yeah, the question was about hyperdepth, how you deal with the just interference from the structured light patterns across multiple lines.
So you can time multiplex the pods, basically. So we use 2 cameras for redundancy. You could just use one. And then we synchronize I didn't mention this, but all the cameras and all the structured illumination are synchronized. So only one illuminator is on at a time. If that's an issue in terms of synchronization, then we did a project a while back that looks at vibrating the actual devices, the actual depth camera that can get rid of the interference across multiple devices. I hope that answered your question.
Yes, thank you.